Hi everyone! In the previous videos we saw how to update our network with the feedforward function, that is the function in charge of updating the neural network. So we see how this function f is applied, also the activation function, and finally the error function that we saw in the previous video. But now we will start to understand how can we decrease the error we calculated in the feedforward. That is the most important thing, because the training process of the network will be to decrease this error. Okay, so here I have put a summary of the previous videos of the feedforward, and here you can see that functions f and g in this case will have this form that we see in the previous videos. This will be the activation function, and finally this will be the way, or the mean square error, to calculate the error that the network has done. So now we will need to decrease the error, and here we will start with differentiable calculus. The idea is that we want to minimize the error. So this will start to be like an optimization problem, where we want to update every weight and bias to decrease this error. So we will be adjusting these weights with differentiable calculus. Okay, so when we have this error, okay, we want to calculate how how sensible a weight is with respect to the error. Okay, so we will need the problem to calculate, to adjust the weights. The problem is to calculate the derivative of the error with respect to each weight. So we want to know how sensible a weight is with the error. Okay, so how do we calculate? We will applying the chain rule. Okay, so every function here we will calculate its derivative, and finally we will calculate this. So the first thing in the chain rule is to calculate, if we want, for example, in the example, we will calculate this value, okay, this way. So to calculate it, we will need firstly to calculate the derivative of the error with respect to the out value of this neuron. So if we put it in a general form, we'll put the derivative of the error with respect to the out of a neuron I, G in this case, because it's the final value of the weight, okay, in the last layer. Okay, so this will be the first derivative, and then we need to calculate this derivative. This derivative will be the derivative of the activation function, okay, that is phi, with respect to the net of GL. And then we are almost done, and now we need to calculate the derivative of the function g, we'll call it g, with respect to now the weight we want to calculate. Okay, so this will be the formula to calculate the derivative of the error with respect to a weight, but only in the last layer, but because in the other layers, like this layer, okay, it will be much complex. Okay, and we will see it in the following videos. So now, how can we resolve these derivatives? So the first derivative is the derivative of the error. If we see the function the error, the derivative here with respect to the out will be in the position that is the out, that is g. We will, the other terms will be constants, and only the term that is this value or this neuron won't be a constant. So the derivative will be dot. Okay, I will put here the derivative of the error with respect to the out, that is this value, in position we put GL, will be 1 divided by n, and then multiply by 2 the derivative of this, that is, this is the variable and this is a constant, so it will be this. Okay, only will be this term because the other terms are constants in this sum. Okay, then so we'll put this here, dot divided by n di minus out of xi in position L. Then this will be very simple, the derivative of this activation function. So we'll put this. Okay. In the logistic function we saw in the previous videos, the derivative, I will put it here for you. Okay, will be, if this is the net value we want to activate, okay, the derivative of this function, we'll put here the net value, will be out of x multiplied by 1 minus out. You can have a paper and see that this is true because everything is math. So now when we have this, we'll calculate the derivative of this, that in this case in the logistic function it will be this. And finally we need to calculate the derivative of the function g, that is here, with respect to the way we want to calculate the derivative. So here, as you can see, this is the formula, and we want to calculate the variable here will be the weight in position here. So this will be a constant, and when we do the derivative we will have only this constant. Okay, so this will be this. Okay, so to improve this I will put the neuron in the previous layer, that in this case it will be this. Okay, so in this example we'll need to do the derivative of this out multiplied by 1 minus out, and then multiply this and the derivative of the error with the neuron, that is this value, and we'll have the derivative of the error with respect to a weight in the last layer. Okay, in the last layer, that is only this layer. So that's all. This is the first important thing in backpropagation, and in the next videos we will see how can we do the backpropagation in the layers that are previous from the last layer. So see you in the next video.